Hi everyone, and welcome to the section 2.7 video. In this video we're going to be diving a little bit deeper into the idea of a derivative, specifically showing how it's a function and how that function connects back to f. We're going to dive a little deeper into that last piece into section 2.8. So we have an example here. Our example function is x squared minus 4. So this is a quadratic that's been dropped down by 4 units on the y. Always good to try to have an idea of the graph of the function that you're dealing with. So okay, remember that we define the derivative of f at a specific value a, so a is a number here, by this limit. All right, so that's just the definition of this idea called the derivative. So the goal here isn't to just focus anymore on a specific a value. It's to try to understand if we can see a general pattern in the outputs we're getting. So I choose an x value. I plug it into this. Okay, it spits out the slope of the tangent line for this function there. Okay, but I change a. What happens next? I change a. I mean, I'm still finding the slope of the tangent line each time. You can still think of it that way. But is there any more I can kind of get out of this? Can I generalize a little bit, like what I'm seeing? And that's the idea here. So we have this little table of a values, and then we want to calculate the derivative at each of these. So right now, all that we have, there's really two ways. We're just trying to do a limit. So let's just set the limit up for this first one. It's the limit as h goes to 0 of f of negative 5 plus h minus f of negative 5 over h, right? Just using this definition, which then is equal to, let's plug in the actual function. This would be negative 5 plus h squared minus 4 minus negative 5 squared minus 4. And don't forget, this is all under the square here, all over h. Now, what we could do, and we'll, we could talk through the steps here, is we could do this limit. Multiply things out, try to see what cancels, what combines, see if you can factor, what's going to happen. Because remember, you just plug 0 in for h, you're going to get 0 on the top, 0 on the bottom, indeterminate. We need to figure something else out. So, okay, what we could do then, if we were feeling a little lazy, is just, go to Mathematica or use a calculator, different calculator, to figure this limit out just numerically, trying to use a table. So we've done that in a separate sheet here. So we've got this table here. So what I did was I put into Mathematica this formula, okay, and then I told Mathematica, all right, I want a to be negative 5, and then I want you to just try a bunch of h values, because remember, taking the limit is saying, well, basically just try a bunch of h values closer and closer to 0 and tell me what happens. So from the right I did some, from the left I did some, and it looks like the value of this inside, right, is going towards negative 10. So the derivative here seems to be negative 10. Okay? All right. Now again, we could just do this out and try to show the same thing. And actually, we're not going to do this one. We're going to do a more general one in just a second, just so we can have it in general, because that's a little bit better than doing each of these individually. So all right, we could do the same exact thing for each of these, and I did do that in Mathematica, and of course the Mathematica file will be available. But what ends up happening, if you keep going through here, is you're going to get a negative 6 here as the derivative at this new point. Okay, here you're going to get negative 2. Okay, here you're going to get 0. Here you're going to get 2. At this one you're going to get 6. And at this one you're going to get 10 as the derivative. So these are the values you get for the slope of the tangent line to this function at each of these different x values. So what we're going to do now is we're going to try to see if we can find a pattern in here, because I see a pattern. And again, the idea is this is supposed to be a function. F prime is a function. So I should be able to figure out some formula such that when I plug negative 5 into the formula, I get negative 10. And you might be like, yeah, it's right here. But I mean without a limit, just like an actual regular old function like we're used to. So this is something that's interesting to do, and I'm not going to make you pick this out and like have to look at these numbers in the future to figure out what the derivative is. You can always just do the limit, like I'll show you in a second, and then in later sections we're going to use rules. But it's an interesting exercise just to kind of try to do it. So let's look through here, and let's try to think of what the pattern is. I plug in -5, I get -10. So there's many different ways you could go from -5 to -10, but just think simply, like what's the ways I could do this? Well, I could take -5 and I could just add -5 to it. That would work. But that doesn't work here, right? -3 plus -5 is -8, so that's no good. So that rule doesn't work. What else could I do? I could multiply by 2. Oh, I just did purple. There's more colors than that. There we go, blue. I could go, you know what? Here to here, let's do times 2. That works. All right, what about here to here? Times 2? Oh, okay, that works. How about -1 to -2? Times 2 works. Times 2, times 2, times 2. Okay, so from that, it seems like if I give you an x value, this is my input, then the output will be 2 times that, which is my formula for the derivative. So what does this mean? Any x value you want to give me, I can tell you the slope of the tangent line to this curve at that x value by just taking the number you gave me and plugging it in here. Just immediately, boom. Works for all these, and it works in general. How do we see that it works in general? Well, we just need to work out this limit in general. So I did an example of this on the section 2.6, 2126 notes, but we'll go through it again. Basically, we're going to define this function as this limit, so just do it. So let's see what happens. So we can start off very similarly to what we did before. So let's do that. Limit as h goes to 0 of f of x plus h minus f of x over h. Again, it's just like we had with the -5s before, but I'm allowing x to be anything now. Any input you want. Okay, so then this was, if we remember our function, x plus h squared minus 4 minus, and then it's x squared minus 4 all over h. And don't forget our limit. That can't go anywhere. All right, so we've got some multiplying out to do, but it's not too bad to multiply this out. Good practice for yourself as h goes to 0. We're going to multiply this out, just this piece here. We're going to get x squared plus 2xh plus h squared minus 4. Now let's go here. Minus x squared, careful with your negative, plus 4. One little mistake and this whole limit gets messed up. All right, let's see if we can combine some terms. I get a positive and a negative x squared. Those cancel. I've got a -4 and a +4. Goodbye. And I'm left with the limit as h goes to 0 of 2xh plus h squared over h. Now, remember, the whole point of this, when you're doing this algebraic manipulation, is you got to get rid of the problem. The problem was, plug 0 in, you get 0 over 0. So you somehow have to get rid of the problem. And the problem is there's basically a copy of h on top and bottom that need to cancel. So with that in mind, hopefully you're thinking like, okay, there's no 1h times here. So let me just make that happen. Factor out an h top and bottom. Remember, don't forget your goal as you're doing a process. So that's h times 2x plus h over h. All right, so those will cancel, and I'm left with the limit as h goes to 0 of 2x plus h. Now, that's just, I can do direct substitution, 2x. Hey, that's what we thought from the table. So there you go. That is my derivative. It's on its own a function. I can graph it. I can do anything I want to it that a function could have done to it that we've learned in the past. All right, so let's graph it, see what happens. So I'm going to take 2x now, and we're going to graph it. So here's a graph of f of x and f prime of x. And it's a little bit weird. You might look at this and be like, oh, maybe I was expecting it to kind of line up somehow better. And I get that. Because when you first learned about f prime, it was a tangent line. And the tangent line would be drawn tangent to the function. And so they fit well together. But this one, it's like, I don't know how this fits. But this actually does fit. And it's going to be very important in the next section. And it's a really important idea to be able to connect these two. What do I mean by that? I mean being able to look at one of these and immediately be able to learn about the other. It's a little crazy that we can do this. I mean, it makes sense, hopefully, with all the math we've done so far. But in terms of just how powerful it is, it's a pretty neat idea. So what we're basically going to be able to do is we're going to be able to say, just right now, pick any point. For example, I don't know, 4. Pick 4. If I was interested in the slope of the tangent line, so what's the slope of the tangent line for f of x? So, okay, that's maybe up here, and I've got, some tangent line. Well, I'll just draw the point bigger so it looks like they intersect. Perfect. Clearly tangent. Yep. So there's the tangent line. What's the slope of this? Well, f prime of 4, which is 8. Done. Okay, but how does this line show that? Well, f prime is right here, right? I want to know f prime of 4, so how do I find out the value of a function at an input? Oh, just plug it in. Boop. 8. So if I'm looking at the derivative, every single value here is just the slope of the tangent line of this function at that same x, right? It's the same x here. So so you should start thinking about okay, so I can see the slope. So here's some of the cool stuff we're going to do in 2.8 that I want you to think about. Let's look at this piece of the graph. Here, I'll draw a little green here so you can see what I'm talking about. So let's think about this chunk of the graph. Okay. All of this, so remember, this is f prime. All of this chunk, not 0. 0 is 0, but everything to the left of 0, right? When x is less than 0, this derivative, okay, all of these blue values here, is also less than 0. Okay, but wait, thinking back about the derivative was the slope of the tangent line. If you're trying to think like real life here, right, that means it's like speed, velocity, it's change, right? It's instantaneous change. So if it's negative, that means that the function must be changing, and changing in some negative way. What does that mean? Well, for a function, it means it's going down. Oh, look at the function, right? We'll keep it green here. If x is less than 0, I immediately, because of this, can say that the function is decreasing. Look, it matches. I'm going down, I'm going down, I'm going down, I'm going down. Of course I am, because this is negative, which is telling me decrease. I'm going down, I'm going down. This is still telling me decrease. I'm going down, I'm going down. Of course you are, because my derivative is down here, and it's a negative number, which says decrease. I'm going down, I'm going down, I'm going down. But hey, look, I'm going down, but kind of slower, right? I'm starting to slow down in terms of this negative slope is starting to get closer to 0, closer to 0. I'm slowing down here. look, it's getting closer to 0, closer to 0. It hits 0. What does my function do? It stopped, right? It hit a minimum, right where my derivative said stop. Okay, now what's the derivative doing here over on this side? My derivative is saying, ooh, positive, I'm positive, I'm positive. So what's my function do? Well, it's a very good listener. It says, oh, derivative, you're positive? Okay, I'll start going up. I'm going to go up. I'm going to go up. And the derivative's like, oh, look, I'm getting even more positive and more positive. And so the function at that same x value is like, okay, I'll go faster. Look at me, I'm increasing faster. And the derivative is like, look at me, I'm getting more and more positive. And they're having fun. So even though they don't look necessarily connected kind of right off the bat, think about how much we can learn from knowing one or the other. And so that's what section 2.8 is going to be a ton of, is trying to do that. And so how do we find the equation of the tangent line then at any x point? Well, what do I need for this? Let's think through what I need. I said line. I immediately need the slope and a point, or an intercept, which is a point. So this is what I need, right? Okay, I can do that. Well, I know that x equals 2, so that's good. So my point is going to be 2, comma, and then I know f, so I can just plug it in. So let's see, what was our function? It was 2 squared minus 4. Okay, which is actually just 2 comma 0, so that's my point. Well, what's my slope here? Well, my slope, f prime of 2, which is equal to, well, it's 2x, right? 2 times 2, which is 4. So I got my two pieces of information. Slope, point. Y minus y1 equals 4, or the slope, x minus x1. Okay, y equals 4x minus 8. That is my tangent line. Look how quick that was. And, ta-da! Looks like B is around 8. It hits the point. And what was our slope, 4? Sure, that's a 4 slope, right? If I'm down at negative 8, go up 4, go up 4. Awesome, I hit 0. Perfect. So again, this red dot here, that is 4 because that's the slope of this tangent line. All right. So this process can be done again, right? We can take a function f and we could go through this process to f prime, and then this was a new function, right? So all you got to do is just forget about this, and look, I can just take a function and do the derivative again, prime prime. And this will end up being just 2. All right? So, okay, now I could do it again, but I'm actually just going to get to 0. And that's going to happen for a lot of functions. Not all of them, but a lot of functions. The polynomials, for example, will all peter out. You could just keep doing derivatives, but eventually they'll go to 0. You could think of a function like sine. That won't happen for, right? Sine, cosine, and of course negatives in there. And then just sine, cos, back and forth. So, you know, there's actually a lot of things you could think about here. But you could keep going. If you like thinking in terms of kind of more real-world stuff, the common thing to think about here is this is position. Think like the height of a ball being thrown, because we've done that example a few times. This is velocity, how fast the ball is moving, and this next one is acceleration. Three, two, one. So that's the connection. And there is actually a third derivative, and that in the physics world is called the jerk of position. So you can just keep going. Keep going. As long as the function remains differentiable, you can continue to differentiate it. All right, and so we've got many derivatives. Keep going. Now, there's other notation to this that you may see. It depends, and there's even more notation depending on what class you're in. Physics classes will sometimes use dot notation. That's supposed to represent a derivative. So just throwing that in there. But we'll often use f prime, or sometimes if we're talking about a function, we say y equals some function. We'll talk y prime. Dy dx is another common one. Df dx if you're talking about a function f, not labeling it y. And then another notation here is d dx of f of x. So these are many different notations. Again, you may see no more. You just have to be careful when you're reading something to pay attention to that notation. And if it's a little different, see if it's defined anywhere. Okay, last thing. 3 ways for f not to be differentiable. Before I just show you the pictures, I want you to think about this. So let's just go back to the definition. Here it is. And let's zoom in. So at a specific a value, we want to know, is the function differentiable? Can I find the derivative? When I do this process, do I get a number out, right? What am I really asking you? I'm really asking you, zoom in, I'm really asking you here, when I take this limit from my function f and my a, whatever they are, does this limit exist? That's what I'm asking you. So when you're thinking about this, it's not like a new thing, it's an old thing. Because what you should be going through your head is, when you're looking at this, is you should be saying to yourself, wait a minute, I know what can happen with limits. It can exist, right? That could happen, and then cool. If it exists, then I'm differentiable at that point. I can do the derivative. But what else could happen? Well, you know, the limit could not exist, but specifically we say it's infinity. That could happen, right? So we could do this limit and it's infinity, which of course doesn't exist, but remember, it's kind of that special kind that we pick out. So what does that mean? It means that somehow we're trying to say the slope of the tangent line is infinity. Yeah, well, yeah, that is what you could see on a graph, and we'll see what that looks like, right? Just kind of think about this in your head if you want. This is a positive slope, okay? And then next to it, it's like, oh, this is like a super positive, big positive slope. Now, keep going like that. And then eventually, if you follow this process, you're going to get to a straight line up. What's the slope of that, right? It's not changing in x. We can't even think about it. That is this infinite case. If you ever are trying to do a tangent line and it looks like you have that vertical slope, which, doesn't really seem to make sense, that's the situation. So we'll see a picture of an example of that. And then what else could happen? I mean, the limit, again, could not exist, and it's not infinity. It breaks because something like the left-hand side, right, as x approaches a from the right, does not equal as you go from the left. Okay? Or if we're using this one, really what we should write is the limit as h approaches 0 from the right doesn't equal the limit as h approaches 0 from the left. Okay, but remember there's that separate definition with x minus a and all that down there where that's the same thing. As you get closer and closer to that point, from one direction you might be getting slopes of these secant lines that seem like they're going towards something, but from another direction it's something different. So, okay, it does seem like there could be 3 of these. So, well, let's see kind of what happens. Let's go down here. All right, so for this first way to not be differentiable, we have a function with a corner in it. So, what's happening here and why at this point A are we not differentiable? Well, what you have to remember is the definition. Right? So let me rewrite it here. It's the limit as x approaches a of f of x plus a minus f of a over x minus a, or, if you prefer, the limit as h goes to 0 of f of a plus h minus f of a over h. So either way is fine. But what we have to remember is, first of all, we're a limit, which means we've got to come from the right and left here. Okay, so as we're getting closer and closer to a, that's what we're doing in both of these scenarios. What are we doing? Well, remember, we're just doing that secant line. So if I take this value here, this first thing, like over here, I'm calculating the slope of this line. Well, it's positive. Okay, so this is some positive slope. Okay, now what's the limit say? The limit's just saying get closer. Okay, I'm getting closer here. All right, now slope of that line. So, okay, it's still positive, right? It's becoming more positive, but okay, whatever, that's fine. It still seems like a number. And then we keep getting closer and closer, and we keep still getting this positive slope here. Now, you're getting these positive slopes, but what's happening on the other side? Let's go over to this other side, right? And we can start looking over here. Like, let's go out over here, and we'll do the secant line. And okay, there you go. Wait, this is a negative slope, right? So this rate of change, this average rate of change, which remember, that's what this inside is. This average rate of change here is negative, but over here it's positive. So if I was to start looking at this in the table, right, let me do one more just so you can keep seeing the pattern. If I was to start looking at this in a table, you're going to notice that I've got a bunch of positive and increasing average rate of change as I get closer to A from the left. But then as soon as I go past A in my table, it'll have gone from a positive and switched to a negative, because these are negative slopes now. So what's that going to tell me? Well, what that's going to tell me in the case of a corner is, the limit as h approaches 0 from the left for this function, whatever this function is, but specifically the average rate of change, so a plus h minus fa over h. So this limit is not going to equal the limit from the right. We don't even need right now exactly what those two limits are. All that's important is we know, right, that from the left we're positive because our slopes are positive, but from the right we're actually negative. And so negative number and positive number are never going to be equal. There you go. So that's a corner. The limit from the left and right don't equal. Okay, so let's go over here. So we also could have a function where there's this jump discontinuity. Now again, this one's, this one hopefully you could see it and think like, okay, yeah, definitely discontinuous. But it's still useful to just go through the idea, right? So again, let's look at that limit as h approaches 0, and we're doing the average rate of change here, f of a over h. So again, you're doing average rate of change, right? So if I come from over here, what's going to be weird about this jump is I'm subtracting f of a, right? So this is, I know this is super weird, but I'm going to go up here. This is again a plus h, but h is negative, which is why I'm left, right? Because, well, left, right, I shouldn't say that. I should say this h is negative because I want to come from the left. And so it's okay to write a plus h here. I'm just taking a negative h. So then, how do I do average rate of change here? Well, it's f of this minus f of this over h, which is really this line. So it's like, oh, that's weird, right? As I keep getting closer now to a from the left, this is super weird to look at, right? As I get closer here, let's go up here, I'm looking now at this line. Like, okay, that's weird. And as I even get closer here, I'm going to get to this weird vertical line where what's the slope of that even mean? So this left-hand limit is not making sense, and in this case, if you try to take this limit all the way, this limit actually won't even exist. It'll go to infinity. So the left-hand limit doesn't even exist. So there you go. The right-hand limit we can talk about. The right-hand side does exist, and you can draw the secant lines here to see that. but they're definitely not equal, and this one from the left doesn't even exist. So no good, not continuous. Limit doesn't exist. Okay. And then we can also have this idea of a vertical tangent. So we've got this function here that has a vertical tangent. And what's that mean? Well, again, it's similar to this, and I even drew them similar colors over here. Not planned, but that's cool. So this vertical line, we can think of this. I mean, I'm not saying that we know the slope, because there's no slope to this, right? How can you talk about change in y over change in x? Does this line, like look at the points on this line. Take any 2 points on this line. What's the change in x? 0. So there's a change in y, so it's number over 0, which is not defined. But what are we usually doing in this case? We think of it like infinity. And we sometimes even call things like that infinity, even though this does not have an actual slope. So we think of this almost like having an infinite slope, a vertical line like this. And so that's just the scenario where your limit, as h goes to 0, of f of a plus h minus f of a over h, this is an infinite limit, right? So that's one thing. We have a jump discontinuity. One of the sides doesn't even exist, the limit. And then we've got another scenario here where, yeah, maybe we could have limits existing, but they're definitely not equal. One is clearly approaching positive numbers, and this one's clearly approaching negative as I come this way. So a couple different ways that you could have a discontinuity that you should be looking out for. All right. Okay, so that's the end of this section. Any questions, of course, let me know, and I'll see you in the next video.